Welcome. Take a moment to settle in without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered or understood or followed to the end. You can fall asleep at any point and you will not miss a thing. Tonight we are going to talk about caves, slowly, without hurrying. Most caves do not announce themselves. The greater part of any cave system lies sealed inside rock, filled with air that has been undisturbed for a very long time, and the only reason any of it becomes known is that somewhere along its length the roof has failed, or a stream has cut down to meet it, or a slope has eroded back far enough to open a hole no wider than a person. The mouth is almost always the accident, the incidental flaw, and it is often the least impressive part of the whole. Cavers speak of entrances that took an hour of crawling before the passage was tall enough to stand in, and of systems many kilometers long whose only known way in is a gap between two boulders on a hillside that a walker would step over without noticing. The landscape that produces caves gives itself away at a distance, once the signs are familiar. In limestone country, the ground has a particular unruliness to it. Shallow bowls in the pasture, stone walls that dip and rise over ground that has settled unevenly, streams that run confidently down a slope and then simply stop, sinking into a bed of gravel with a faint noise and going nowhere visible. The rock itself weathers into pale ribs and clints, split by deep grooves where rainwater has run along the joints for tens of thousands of years. Valleys often lack rivers because the water that once carved them has since found a route underneath and abandoned the surface course. In places, the whole drainage of a district happens out of sight, and the only water to be seen is in springs at the foot of the hills, arriving cold and clear and in surprising volume. Sinkholes are the most familiar way that a cave first becomes known, and they arrive without much ceremony. A farmer walks a field that has been walked for generations and finds a hole in it, perhaps a meter across, sometimes considerably more, with grass hanging over the rim and a heap of soil visible at the bottom. What has happened is that a void in the limestone beneath has been quietly accepting the soil above it for years, grain by grain, carried down by percolating water, until the arch of packed earth over the void could no longer support itself and dropped through. Such collapses tend to follow heavy rain, or a sudden drop in the water table, or a change in how water is routed across the surface, and they happen under roads and gardens as readily as under fields. In most cases, the hole leads to nothing but a small chamber choked with fallen material. In a small number of cases, it opens on air that is moving, and moving air is the single most reliable indication that there is space beyond. The draft is the classic sign, and it is a matter of straightforward physics. The temperature deep inside a cave settles at close to the annual average of the surface above it, and stays there, varying only slightly through the year, because rock is a poor conductor and the seasons never really reach far inside. The air outside, meanwhile, swings across a range of many degrees. In summer, the outside air is warmer and lighter than the cave air. So the cool, dense air inside the cave drains out through any low opening, and a person standing at the right spot on a hillside on a hot afternoon can feel cold air pouring out over their boots. In winter, the relationship reverses, and the cave draws air in at the low entrances and exhales it at the high ones, which is why some holes appear to breathe outwards in one season and inwards in another. Where a system has two openings at different heights, the effect is stronger because the difference in air density over that vertical distance behaves like a chimney, and the flow can be strong enough to be heard as well as felt. Prospectors for new caves make deliberate use of this. They walk hillsides in the hottest part of summer with their hands low, feeling for cold spots where a scree slope or a bramble thicket is venting air. And they walk the same hillsides on the coldest mornings of winter looking for the opposite sign, which is more visible than tactile. Warm, moist air leaving a cave on a freezing day condenses as it meets the outside, so a hole that would otherwise be invisible produces a small plume of mist. And the ground around it stays clear when everything nearby is white with frost or covered in snow. Patches of bare earth in a snowfield have led to a good many discoveries. So has the reverse arrangement in summer, where cold air escaping keeps a small area damp and green while the slope around it dries out, or supports mosses and ferns that have no business growing on an exposed south-facing hillside. Vegetation more generally is worth reading. A ring of nettles or a single clump of trees in the middle of otherwise even grazing often marks an old shake-hole where soil has gathered and stock have not troubled to graze the steep sides. Ash and hazel take root along fissure lines. In tropical karst, the pattern is different again, with dense vegetation crowding the rims of collapse features that open into daylight shafts hundreds of meters across, so that the first sign of a cave may be a change in the canopy seen from a ridge or from the air. Where limestone hills have been quarried, faces sometimes cut clean through a passage and leave it hanging in the rock wall, and quarry workers have opened a fair share of the known caves of Europe in this accidental way, occasionally to the frustration of the quarry, which then has to deal with an unstable void it did not plan for. Animals have been useful indicators for as long as people have looked for caves. Bats leaving at dusk in a rising column give away the position of an opening that may be screened by scrub, and their arrival and departure can be watched from a distance with no need to approach. Swifts and swallows nesting in the entrance zone, foxes and badgers using the sheltered lip, and in some regions the presence of particular insects that congregate in the cool mouth, all indicate depth beyond. In older accounts, the discovery of a cave is often credited to a dog going down a rabbit hole and not coming back. And while the story has been repeated often enough to become a convention, the mechanism behind it is sound, since animals find small openings that people walk past. Water is the other great guide. Wherever a surface stream sinks, there is a passage taking it, although whether that passage is large enough to follow is a separate question, and many sinks are simply beds of rubble through which the water filters. Wherever water reappears in a spring or resurgence, there is a system upstream of it, often a long one. The relationship between the two ends can be established by tracing, which came into use in the 19th century and remains standard, and the results have repeatedly shown water traveling further and faster underground than anyone expected. Attention naturally concentrates on the ground between a known sink and a known rising, since anything found there is likely to connect. A great many entrances are not found so much as made. Cavers speak of digging as a discipline in its own right, involving years of work at a promising drafting hole, moving stones and mud upwards through a shaft in buckets, shoring the sides with scaffolding and timber, and occasionally blasting where the law and the rock allow. Some digs are abandoned. Some are worked by the same small group of people across 2 or 3 decades, on the strength of a steady breath of air and nothing else, and then open into passages that run for kilometers. The lore of British and European caving in particular is full of these long, patient projects undertaken at weekends in the rain, at sites that look from the surface like a hole in a field with a lid on it and a pile of spoil beside it. Once found, an entrance tends to be modest about what lies beyond. A crawl may lead to a shaft of 200 meters. A gap under a boulder may open into a chamber whose far wall cannot be reached by lamplight. The connection between the size of the mouth and the size of the cave is close to none, and the first descent must be made before anyone knows which sort of hole has been found. In the second half of the 19th century, when the systematic exploration of shafts began in earnest in France, in the Austrian lands and in the limestone hills of northern England, the descent of a vertical pitch was as much a matter of surface organization as of anything happening below. A tripod or a pair of stout timbers would be set over the mouth of the hole, a windlass or a pulley block lashed into place, and a team of men, often hired locally for the day, would take up position on the rope. The explorer sat in a loop of rope or a plank sling, sometimes with a light lashed to the harness, and was let down by hand at whatever speed the surface party judged reasonable, spinning slowly, fending off the walls with boots and elbows, unable to see the floor and unable to be heard once the sound of falling water filled the shaft. A thin cord was often taken down alongside the main rope, so that signals could be pulled through it, and in some of the more elaborate operations, a field telephone was carried down and connected to a set on the surface, which allowed the man on the rope to say plainly when he wanted to be lowered further and when he wanted to stop. The best documented of these campaigns are those of the French pioneer Édouard Alfred Martel, who worked through the 1880s and 90s with a portable outfit that he refined from one season to the next, and which included rope ladders, sounding lines, thermometers, and collapsible canvas boats that could be carried in pieces down a shaft and assembled on an underground river. He descended the great shaft of Padirac in the Dordogne region and worked the passages beyond it by boat. And in the summer of 1895, he was lowered into Gaping Gill in the Yorkshire Dales, where a stream falls freely for something over 100 meters into a chamber floored with boulders and mud. The diversion of the surface stream, the setting of the tackle, the timing of the descent, and the discipline of the men on the rope mattered as much to the outcome as any courage in the sling. Martel wrote his methods down at length, and much of the equipment list that later generations inherited can be traced to those accounts. What the early explorers wore was, by any later standard, unsuited to the conditions and worn anyway. Wool jerseys and jackets, moleskin or corduroy trousers, oilskins or waxed canvas for the wettest pitches, and boots with hobnails or clinker nails hammered into the soles for grip on wet rock. Wool has the useful property of retaining some warmth when soaked, which is why it lasted so long underground. But a man in wet wool under a waterfall in a cave held at 8 or 9 degrees loses heat steadily and without much warning. And a great many early descents were cut short not by the difficulty of the rock, but by cold. Hats were felt or leather, later reinforced, and the modern combination of a hard shell helmet, a synthetic pile undersuit, and a waterproof oversuit of coated fabric only settled into general use in the second half of the 20th century, borrowing from mountaineering, from mining, and from the diving trade in roughly equal parts. Light was the constant problem. Candles were carried in bundles, wedged onto rock ledges, set in tin holders, and in some caves the smoke marks of their use are still visible on low ceilings. Torches of resinous wood, oil lamps with wicks, and short-lived flares of burning magnesium ribbon used for photography all had their place, and each of them shared the same weakness, which is that a flame needs to be sheltered from draft and from water, and that both are common underground. The lamp that changed the character of exploration for several decades was the acetylene lamp, in which water drips onto lumps of calcium carbide in a sealed lower chamber, generating acetylene gas that passes through a jet and burns in front of a polished reflector. Miners had used these lamps first, and cavers adopted them because they were light, because the fuel was compact and cheap, and because the flame threw a soft, wide light that showed the shape of a chamber rather than a bright disk on one wall of it. Working an acetylene lamp was a small trade in itself. The jet blocked with carbide dust and had to be cleared with a fine wire kept for the purpose. The water feed had to be adjusted so that the flame neither guttered nor roared, and the spent carbide had to be dumped and replaced at intervals of a few hours, which is one reason older cave passages sometimes have small grey heaps of exhausted lime beside the route. The lamp smelled distinctly of garlic, it warmed the hands on a long wait, and its flame gave notice of foul air by burning low. It also left soot on the ceilings and lime on the floors, which is why carbide has been given up in decorated and archaeologically sensitive caves, and largely given up elsewhere as electric light improved. Lead-acid cells worn on the belt with a bulb on the helmet came in from the mines, then sealed cells and rechargeable batteries, and eventually light-emitting diodes, which draw so little current that a caver can now carry 3 independent sources of light and days of burn time in the volume once taken up by a single lamp and its spare fuel. The convention of never entering a cave with fewer than 3 separate means of making light is older than the electric era and has survived it intact. Descent itself was, for a long time, made on ladders. Knotted ropes were used at the beginning and are exhausting to climb on and unforgiving of a slip, so hemp rope ladders with wooden rungs came into use, heavy when dry and much heavier when wet, and prone to rot in store. These gave way to ladders built from flexible steel wire with light alloy rungs swaged onto them, which could be rolled into a compact coil, carried in a canvas tackle sack, and hung down a pitch from an iron bar or a spike wedged across the shaft. A ladder pitch was climbed with a separate rope tied to the climber and belayed by someone above, so that 2 people were always occupied at each drop, one on the wire and one on the lifeline, and the party moved through a deep system in a slow relay of sacks and belays. In the deep shafts of the Yorkshire Dales and the Alpine Plateau, this arrangement worked, but the weight told against it, since a single deep pitch needed several ladders joined end to end, and an expedition into a system of many hundreds of meters depth could find itself carrying a load of steel that no small team could move far. The alternative had been available in principle since climbers learned to slide down a rope and to climb back up it with friction hitches, the best known of which is named after the Austrian climber who described it, and which grips the rope when loaded and slides when relieved. From the middle of the 20th century, cavers in the southern United States and in France worked out the elements of what came to be called single rope technique, in which one rope hangs down the pitch and is used both for descending and for ascending. The caver descends on a friction device, a rack of alloy bars, or a pair of grooved bobbins in a metal frame, controlling speed by the amount of rope wrapped through it, and climbs back on mechanical ascenders with toothed cams, one attached to the harness and one worked with a foot loop in a steady sitting and standing rhythm. Rigging became the skill on which everything else depended, where the older ladders hung more or less where the shaft allowed. A rope must be kept away from any edge that would abrade it and out of the fall of water where possible. So pitches came to be broken into stages by intermediate anchors, with the caver stopping in mid-shaft to change from one length of rope to the next, and with sideways deviations pulling the rope clear of rub points. Anchors were placed in sound rock with expansion bolts or resin, in positions chosen and often left in place for those who followed. And the older nylon ropes with their generous stretch gave way to low-stretch kernmantle ropes with a woven sheath around a parallel core which hold their length under load and can be inspected along their whole surface for damage from grit and mud. A rigged pitch gets a caver to the bottom of a shaft, and a strong party with good lights can travel a long way through unknown passage in a single day. But until the passage has been measured, it remains a memory rather than a place, difficult to describe to anyone who was not present and impossible to compare with anything else. Among cavers, there is an old and unsentimental attitude on this point, expressed in various forms, which holds that passage which has not been surveyed has not really been discovered. And while the sentiment is partly a matter of club pride, it also reflects something practical, because the map is the only means by which the shape of a cave can be held in one piece, examined at leisure, laid alongside the surface landscape, and handed on to people who will go back into it years later, looking for the places where it might continue. The method at its core is simple and has not changed in principle for well over a century. The surveyors choose a point on the floor or the wall, call it a station, and from that station they measure to the next station 3 quantities. The distance between the two, the compass bearing from one to the other, and the angle of inclination, up or down, along the same line. These 3 numbers describe a single leg in 3 dimensions, and a chain of such legs, added one to the next, traces the course of the passage away from the entrance and down into the hill. Everything else in cave surveying is a refinement of that chain, or a means of guarding it against error, or a way of hanging the shape of the passage onto it. The distance was long measured with a tape, a fiberglass or steel band marked in meters and feet, held taut between 2 people and read at the station mark, and tapes remain in use because they are cheap, and they fail slowly and obviously. In France and elsewhere, the thread counter became popular, a small device holding a spool of light cotton line whose passage over a toothed wheel turns a counter, so that the surveyor at the forward station simply reads the number of meters of thread paid out behind them, leaving the thread in place as a visible record of the survey line along the floor. From the late 20th century, the laser distance meter arrived, borrowed from the building trade, and in a modified form that incorporated an electronic compass and inclination sensor into the same handheld body. It allowed the three measurements to be taken with one press of a button and stored in memory or sent directly to a small computer, which removed a great many of the copying mistakes that used to creep into notebooks. Before that, and still today alongside it, the bearing and the angle came from a sighting compass and a clinometer, instruments about the size of a matchbox, held to the eye and read through an internal lens against an illuminated scale, with the card damped in fluid so that it settles quickly in a cold hand. Some models combine both functions in one housing, others are carried as a pair on a cord around the neck. They are sighted on a light held at the next station, which in practice means that survey work is done in a rhythm of small negotiations. The person at the far station holding still and shading their lamp. The person at the instruments waiting for the card to stop swinging. The numbers read aloud, repeated back, and written down. Choosing where to put the stations is the part that experience improves most. A leg wants to be as long as the passage allows, because fewer legs mean fewer accumulated errors. But it must also be a clear line of sight, and it must not be so long that the sketch of the passage between the two ends becomes guesswork. In a straight railway tunnel of a passage, the legs might run for 20 or 30 meters. In a tight winding rift, they may be reduced to 2 or 3 meters each, and 100 meters of cave can swallow an afternoon. Stations are marked so that they can be found again, with a small cairn of stones, a spot of paint, or a dot on a piece of tape, sometimes with the number written beside it, and the best of them, at junctions and at the tops and bottoms of pitches, become permanent references for decades of later work. The chain of legs gives a line, and the line by itself would describe a wire hanging in the rock, so the passage has to be drawn onto it. At each station, the surveyors record how far the wall lies to the left and to the right, how high the ceiling stands, and how far the floor drops below. 4 numbers that fix the cross-section. And one of the party sketches the passage in a notebook, in plan and usually also in profile, drawing the walls between the stations, the shape of the boulders, the line of the stream, the banks of sand, the places where the ceiling comes down, standard symbols developed for this, hatching for a slope, small circles for cobbles, arrows for the direction of flow, so that a sketch drawn by one person can be read and inked by another. The books are made of waterproof paper, written on in pencil because ink runs, and they come out of the cave crumpled and grey with mud, still legible. Survey trips are, by long agreement, colder and slower than exploration trips. The party stands still for much of the time in a draft or a stream, one person holding the tape end, one reading instruments, one writing and drawing, and the work advances in the 20 or 30 meter increments of the legs. Numbers are called and repeated in a fixed order to avoid confusion between a bearing of 180 degrees and one of 80, and inclinations are always stated with their sign. Where the line must be taken up or down a pitch, the measurement is made along the rope or the plumb of a weighted cord, and the surveyors record whether the top station is at the lip or set back from it, because the difference matters when the survey is later joined to a passage above. Error is the constant subject of attention. A compass reads magnetic north, which differs from true north by an amount that varies with place and drifts slowly with time, so the declination must be recorded and applied. Steel spoils a compass, which is why survey parties keep tools, carabiners, and lamp batteries away from the instruments, and why in some caves with mineralized or iron-rich rock, the readings are treated with suspicion. Instruments are calibrated against known lines on the surface. Readings are often taken both forward and backward along the same leg, so that the two can be compared. And where the survey passes through a loop of passage and returns to a station already fixed, the amount by which it fails to close exactly gives a direct measure of the accumulated error, which can then be distributed mathematically around the loop. Formal grading schemes were drawn up. Most familiarly, a scale running from a rough sketch made from memory up to a survey made with calibrated instruments and stated tolerances, so that a map can declare how much confidence its lines deserve. Turning notes into a drawing was once a matter of trigonometry done by hand. Each leg reduced to a horizontal length and a vertical rise, then plotted on gridded paper with a protractor and scale rule, station by station, before the sketch detail was inked around the plotted line. Large systems were drawn in long strips that could be joined, and the master sheets were kept, corrected, and added to for years. From the 1960s and 70s, the reduction, addition, and adjustment moved onto computers, first as batch calculations that returned lists of coordinates, and later as programs that both adjust the loops and draw the passage outlines, producing plans, extended elevations, and rotatable three-dimensional line plots which show at a glance the levels of a cave and the way it has developed along particular sets of joints. Tying the underground survey to the surface added another dimension. Entrances can be fixed accurately by satellite positioning, and a technique called radiolocation, in which a transmitting loop is laid flat on the cave floor and its field detected and centered from above, allows a point deep inside the cave to be pinned to a spot on the hillside and its depth calculated. That is how surveyors confirm that a passage runs beneath a particular valley, or under a road, or within a few meters of another passage known from a different entrance. And it is how the likely sites of new entrances have often been identified for digging. The accumulation is slow, and it is cumulative. An enslaved guide at Mammoth Cave in Kentucky, named Stephen Bishop, drew a map of the passages he had explored from memory that was published in the 1840s, and it remains recognizable against modern plans of the same passages. More than a century later, in 1972, a connection was made between the Flint Ridge system and Mammoth Cave itself, and the joined survey became the longest known cave in the world, a position it still holds with a measured length of well over 600 kilometers, gained in kilometer and 100-meter pieces across generations of survey trips. In the Alps, the Hulloch in Switzerland was surveyed steadily through the 20th century into a system of comparable scale. In the gypsum of the western Ukraine, immense flat mazes were mapped, passage by identical passage. Under the Yucatan, divers surveying flooded galleries with reels of knotted line, a compass and a slate strapped to the forearm have joined system to system until the mapped totals rival anything on dry land. What the maps then do is generate the next round of exploration. A plan showing all the known passage in a district reveals blank spaces, alignments that beg to be extended, two dead ends approaching one another with 50 meters of unmapped rock between them, and levels that repeat at the same altitude, from cave to cave and hint at old water tables. The survey, begun as a record of where people had already been, becomes the instrument by which they decide where to go. And the notebook full of muddy numbers turns out to be the part of the trip that lasts. In 1879, on a hillside in northern Spain near the town of Santillana del Mar, a landowner named Marcelino Sanz de Sotuola was digging in the sediment just inside a cave that local people had known about for some years, looking for the flint tools and animal bones that were then beginning to be recognized as the debris of very ancient human life. His young daughter Maria was with him, and it was she, small enough to stand upright where he had to stoop, who looked up at the low ceiling of a side chamber and saw the shapes of animals in red and black above her. The bison of Altamira are painted on a rock surface that in places is barely 1.5 meters from the floor, arranged around the swellings and hollows of the limestone so that the curve of a haunch follows the curve of the rock. Sotuola published a short account the following year, arguing that the paintings belonged to the same remote period as the worked flint and the engraved bone he had found in the floor deposits. And the argument was received by most of the prehistorians of the day with polite disbelief. The objections were not unreasonable in the state of knowledge at the time. Nothing quite like the ceiling was then known. The pigments looked fresh, and there was a suspicion, voiced openly at an international congress in Lisbon in 1880, that a local artist had been at work. Sotuola died in 1888, with the question unsettled. What changed the verdict was not new argument, but new caves, and in particular, caves where the images lay behind sediment that had plainly taken thousands of years to accumulate, or were covered by a film of calcite that had grown over them since they were made. At La Mouve, in the Dordogne in 1895, engravings were exposed only after the removal of a deep fill that had sealed the passage. In 1901, 2 more decorated caves came to notice in the same district, Font de Gaume with its painted bison and Les Combarelles with its engraved walls, both examined by local school teachers and specialists who could no longer treat the finds as isolated. The following year, Émile Cartellac, who had been among the doubters, published a short paper acknowledging his error, and the authenticity of Paleolithic wall art passed from dispute into fact. Lascaux came to light in September 1940, near Montignac in the valley of the Vézère, when 4 teenagers investigated a hole in the ground on a wooded hillside where a tree had come down and the soil had slumped. The shaft they widened dropped into a chamber whose walls carried aurochs, horses and deer at a scale that had no precedent, some of the bulls more than 5 meters long, drawn with a confidence of line that has kept people arguing about it ever since. The cave was studied by the Abbé Henri Bruy, who had already spent decades in the decorated caves of France and Spain, and after the war it was open to visitors on a scale it could not sustain. The breath and body heat of many thousands of people a year, together with the lighting and the alterations to the entrance, changed the air chemistry and the humidity, and algae and mineral films began to spread across the painted surfaces. Lascaux was closed to the public in 1963. A facsimile of the main chambers, built from surveyed measurements and molded surfaces, opened nearby 2 decades later and has since been extended, which is now the usual accommodation between a fragile cave and the wish of people to see what is in it. Discoveries have continued at intervals through the 20th century and into this one. In 1985, a diver named Henri Cosquer swam into a passage in the limestone cliffs east of Marseille, whose entrance lies some 37 meters below present sea level, and followed it upward for well over 100 meters to chambers that are still above water, where he eventually found painted and engraved horses, ibex, bison, seals, and seabirds. When the images were made, the sea stood far lower and the cave mouth was well inland. In December 1994, 3 cavers working in the Ardèche Gorge opened a narrow way into a large system whose walls carried charcoal drawings of lions, rhinoceroses, mammoths, and bears, along with hand stencils and bear scratches and radiocarbon measurements on the charcoal, placed some of the drawing well beyond 30,000 years ago. The floor of that cave had been left largely undisturbed, so the footprints, the hearth charcoal, and the bear hibernation hollows survived alongside the images, and the decision was taken from the outset to keep human traffic to a minimum, with access limited to a small number of researchers on strictly controlled visits. The materials themselves are simple and local. Red comes from iron oxides, chiefly hematite, ranging through orange and brown according to the mineral and its heating. Yellow comes from goethite and related earths. Black comes either from charcoal, which can be radiocarbon dated, or from manganese oxides, which cannot. White is more rarely used, from clay or from calcite. Grinding stones with pigment still in their hollows, lumps of ochre with facets worn on them, and shallow cups of stone or bone have been recovered from cave floors near the painted walls. The pigment was applied dry as a crayon or wet as a paste with water and perhaps other binders, or blown, and the blowing accounts for the soft-edged fields of color and for the hand stencils made by placing a hand flat on the rock and spraying pigment around it so that the shape is left in reserve. Hand stencils occur in caves in France and Spain, and also in forms of comparable antiquity in caves on the islands of Southeast Asia, where mineral crusts over the images have yielded ages of at least 40,000 years. Technique in the caves is not confined to paint. Engraving with flint burins covers whole walls at some sites layer upon layer, so that individual animals can be hard to separate from the tangle of lines. Where the rock is coated in the soft white paste called moon milk, images were drawn simply by dragging fingers through it. And at Rouffignac, such finger drawings and painted mammoths run for hundreds of meters into the hill. Elsewhere, the natural relief carries much of the work. A bulge in the wall becomes the shoulder of a bison, a crack becomes a back line, a nodule becomes an eye, and the artist supplies only what the rock does not. At Lascaux, rows of sockets cut into the walls of one gallery show that scaffolding was erected to reach the upper surfaces, and shaped stone lamps have been recovered from the same cave. Small hollowed pieces with residues of fuel in them, which together with torches of resinous wood account for the light by which all of this was done. The placement is as consistent as the subjects. Some panels lie in daylight or twilight near the entrance, but a great many are deep inside, beyond several hundred meters of passage, in chambers reached by crawling, by climbing, or by wading, and a proportion are in niches so tight that only one person at a time could have seen the image from any useful distance. Animals dominate the subject matter, chiefly the large herbivores that were hunted or lived nearby. Horses, bison, aurochs, deer, ibex, mammoths. Along with the predators, lions and bears and rhinoceroses, more common in some caves than others, human figures are scarce and usually schematic. Dots, lines, grids, and other geometric signs appear in most decorated caves, sometimes in ordered groups, and their meaning remains open. Dating has advanced on two fronts: radiocarbon on charcoal drawings and on the charcoal of nearby fires, and uranium series measurement of the thin calcite crusts that grow over painted surfaces, which gives a minimum age for whatever lies beneath. Applied to a red disc at El Castillo in northern Spain, that second method returned an age in excess of 40,000 years. Applied across a single cave, both methods show that many decorated caves were not the work of one visit or one generation, but were entered, marked and re-entered over spans of thousands of years, which places the ceiling that Maria Sanz de Sotuola looked up at into a tradition long enough to make the modern history of its recognition, from disbelief to facsimile, look brief. A cave floor is not, in most cases, the bedrock on which the passage was cut. It is a slow accumulation of whatever the cave has been given. Silt dropped by floodwater, sand carried in and abandoned, clay that settled in still pools, fragments of roof that fell and lay where they fell, calcite that spread across the surface and set hard, dust blown in through the entrance, leaves and twigs washed down a slope, guano beneath a bat roost, bone, charcoal, and the trodden mess of things that walked there. Because the air inside a cave is stable, because the temperature holds close to the mean annual temperature outside, and because sunlight and frost and wind never reach beyond the first stretch of passage, these accumulations sit undisturbed for periods that on the surface would be unthinkable. A hillside erodes. A cave floor tends to gather. The result is that caves hold a disproportionate share of what is known about the last few 100,000 years of animal and human life in temperate regions, not because more happened in them, but because less was subsequently removed. Excavators speak of the deposit rather than the site, and read it from the top down as a sequence of layers, each representing a period of accumulation under particular conditions, separated sometimes by sharp boundaries where the regime changed, sometimes by gradual transitions, and sometimes by a sheet of flowstone that sealed everything beneath it and can be dated in its own right by the uranium and thorium in its calcite. A flowstone floor is an inconvenience to dig through and a gift to interpret, since it gives a firm ceiling of age for the layers below and a firm floor for those above. Among the most common contents of European cave deposits are the remains of the cave bear, an animal larger than a brown bear that used caves for winter dormancy over many tens of thousands of years and died in them in great numbers. The pattern of death is unremarkable once explained. A bear that entered a passage in autumn, having failed to build sufficient fat reserves, or a cub born during the winter to a mother in poor condition, or an old animal in its last season, simply did not come out again, and the body remained in the dry, cool, scavenger-poor interior where it decayed slowly and was gradually covered by the sediment that continued to arrive. Repeated across thousands of winters, this produces bone in quantity, distributed through the layers rather than heaped in a single event, and often concentrated in the sheltered side chambers where the animals preferred to lie. The hibernation hollows themselves survive in some caves as shallow circular or oval depressions in soft floor sediment, scraped out and worn smooth, sometimes with a raised rim of displaced material, and sometimes in clusters where the floor was suitable. Alongside them are found other marks made by bears going about ordinary business, long parallel scratches on clay walls where claws were dragged, polished patches on rock at bear height where flanks rubbed as animals passed the same constriction year after year, and muddy smears well above the floor. Chauvet in the Ardèche is often cited for the abundance and clarity of these traces, with hollows, scratch marks, and skeletal remains lying in the same chambers as painted panels, so that the cave records two very different kinds of occupation with no clear evidence that the two ever met. Cave lions turn up far less often, which is consistent with the general rule that predators are rarer than their prey, and that a predator hunting across open country has fewer reasons to die in a cave. Where lion bones do appear, they are usually scattered rather than articulated, and their presence has been used to argue for occasional denning, occasional scavenging visits, and occasional bad luck at the bottom of a shaft. Vertical entrances are among the richest bone sites of all, because a shaft that opens at ground level in a wooded landscape functions as a trap that operates continuously without maintenance. Animals fall in, cannot climb out, and accumulate at the base in a jumble that mixes species which never shared a habit, alongside the bones of the smaller creatures that fell in after them, and the owl pellets and rodent remains that arrived by other routes. The small bones matter more than their size suggests. Voles, shrews, bats, lizards, frogs, and fish have narrow environmental preferences and short generation times, and their teeth and jaws are durable and identifiable to species, so a sieved sample of sediment from a single layer can indicate whether the surrounding landscape was forest or steppe, whether the winters were severe, whether there was standing water nearby. The pattern of species through a sequence of layers becomes a record of climate change at the scale of the cave's own catchment, independent of the isotope records read from ice and from ocean cores, and frequently in agreement with them. Softer material survives in more specific circumstances. Footprints are preserved where a surface of fine wet clay or sandy silt was walked on and then left alone, protected from dripping water, from flooding, and from later feet. In the extension of Neo known as the réseau clastres, human prints lie in soft floor sediment beyond the decorated chambers, and comparable traces are recorded in other French and Spanish caves, sometimes as bare footprints, sometimes as the drag marks of torches, sometimes as the four-clawed prints of bears crossing the same ground. Interpreting them is a matter of careful geometry rather than intuition, and specialists in modern tracking have been brought into a number of caves to assess stature, gait, direction of travel, and the number of individuals involved. The conclusions are usually modest: a small group, a child among adults, a route taken once, and their value lies in the fact that a footprint records a few seconds rather than a season. Charred plant material survives because charring makes it chemically inert. Wood that burns incompletely becomes charcoal and can be identified to genus by the anatomy of its cells, which reveals what fuel was gathered and therefore what grew within walking distance. Seeds and nutshells that fell into a fire and were charred rather than consumed can be recovered by flotation, in which excavated sediment is stirred into water so that light carbonized fragments rise and can be skimmed off through fine mesh. In dry caves, in arid regions where no water passes through the deposit, preservation extends much further and uncharred plant material survives, along with fiber, cordage, basketry, and the desiccated dung of animals that sheltered there, so that meals and manufacture can be reconstructed in detail that is unavailable anywhere in a wetter climate. Fire itself leaves a layered signature that can be read in thin section. A hearth used in place typically shows a reddened, heat-altered base where the underlying sediment was oxidized, a dark band of charcoal above it, and a pale grey or white band of ash, which is largely calcium carbonate derived from the burnt wood, and which under the microscope preserves the boxy crystal pseudomorphs that form in wood cells. When those layers appear in that order, undisturbed, the fire burned where it is found. When ash and charcoal appear mixed together in a lens with no reddened base, the material was probably raked out and dumped, which is itself informative about how the space was organized. Stacked sequences of hearths, one above another across many layers, indicate that a particular spot was chosen repeatedly, often near a wall, out of the draft, at the edge of the daylight. None of this reads cleanly. Bears digging hibernation hollows churn the layers they lie in, and so do badgers, hyenas, rabbits, and, in later periods, people quarrying cave earth, 19th and early 20th century digging for bat guano and for nitrate-rich sediment, removed the upper deposits of many caves entirely before anyone thought to record them, and antiquarian excavation, aimed at collecting bones and worked flints rather than understanding their arrangement, destroyed the stratigraphic information that would now be considered the more valuable half of the find. Modern practice is correspondingly conservative. Sections are left standing, small areas are excavated slowly, sediment is sampled for microscopic and chemical analysis, as well as for objects, and increasingly for fragments of ancient DNA that survive in the sediment itself, bound to mineral grains in caves where no bone at all has been recovered. Deposits are also, wherever possible, left in the ground on the reasoning that a layer removed is a layer read once, and a layer preserved can be read again by methods that do not yet exist. The passages themselves, the floors and the sediments they hold, exist because one common rock will quietly go into solution in ordinary water. Most of the world's caves are formed in limestone, and limestone is calcium carbonate, accumulated on the beds of shallow seas from the remains of things that built their skeletons out of it. Corals and shellfish, and the microscopic plates of single-celled algae, along with grains precipitated directly from warm water. Those deposits were buried, compressed, and cemented into rock, and in the process they acquired the layering that later becomes so important, because a limestone is rarely uniform. It is a stack of beds, some thick and some thin, separated by surfaces where sedimentation paused or changed, and those surfaces are planes of weakness. Later, tectonic movement lifted the rock above sea level and bent and broke it, adding a second set of weaknesses in the form of joints and faults cutting across the bedding. What that leaves, when rain begins to fall on it, is a soluble solid divided by a three-dimensional net of narrow cracks. Pure water, on its own, does very little to limestone. It will dissolve a small amount and then stop, saturated. And if that were the whole of the chemistry, there would be very few caves. What changes the outcome is carbon dioxide. Rain falling through the atmosphere takes up a little of it, and some of the dissolved gas reacts with water to form carbonic acid, a weak acid that is nevertheless strong enough to attack carbonate. Rainwater arriving at a bare limestone surface is therefore mildly aggressive, and over long spans it will etch and round and fret that surface into the runnels and fluted blocks familiar from exposed limestone pavements. The more consequential source of carbon dioxide lies just below, in the soil. Plant roots respire, and bacteria and fungi break down leaf litter and dead root material, and both processes release carbon dioxide into the air held between soil particles. The concentration there is far higher than in the open atmosphere, commonly by a factor of tens, and in warm, wet, well-vegetated ground higher still. Water percolating through that soil equilibrates with the enriched air before it ever reaches the rock, and it arrives at the bedrock, carrying several times the acidity it had as rain. This gives soil and vegetation a curious role in the making of caves. Bare, cold, thinly vegetated karst dissolves slowly. Karst under a deep soil and a forest dissolves faster, and much of the hollowing out of a limestone hill can be attributed to chemistry that begins in the top meter of ground, in the dark, among roots. The reaction itself is simple enough to state. Calcium carbonate, water and carbon dioxide combine to give calcium ions and bicarbonate ions, both of which stay in solution and are carried away. Water in a temperate karst spring typically holds a few hundred milligrams of dissolved limestone in every liter. Invisible, tasteless to most palates, detectable as hardness when the water is boiled. The reaction is reversible, and that reversibility matters, because when such a water later loses carbon dioxide to cave air, the equilibrium shifts back and calcium carbonate is deposited again, which is why the same chemistry that empties a cave also decorates it. Temperature enters the balance as well, in a direction that is easy to get backwards. Cold water dissolves more carbon dioxide than warm water, so cool, wet climates, given vegetation and soil, are efficient at cave making, and much of the classic karst of Western Europe developed under conditions no warmer than the present. There is a further mechanism that explains a good deal of what is found deep underground. Two waters may each be fully saturated with dissolved limestone, yet hold different amounts of carbon dioxide, and when they mix, the resulting blend is no longer at equilibrium. It becomes capable of dissolving more rock. This mixing corrosion means that dissolution does not simply cease once water has traveled some distance from the surface. At junctions where separate flow paths meet, deep in a system, the water can be renewed in its aggressiveness, and the enlargement of passages continues far from any soil. Getting the acid to the rock is a matter of plumbing rather than chemistry. Limestone itself, once cemented, is often nearly impermeable, so water does not seep through the body of the rock in the way it moves through sandstone. It moves along the fractures, and at the outset those fractures are narrow, apertures of a fraction of a millimeter, along which flow is slow, smooth, and laminar. Water entering such a crack dissolves rock most vigorously near the input, becomes progressively closer to saturation as it travels, and may be entirely spent long before it emerges. The result is a very slow widening, concentrated at the upstream end, and for a long time nothing that anyone would call a cave. What resolves this slowness is competition. A hillside contains a great many fractures, and they are not identical. Some are marginally wider or more directly aligned with the hydraulic gradient, or better connected to a sinking stream. A slightly wider fracture carries more water, and more water means the flow stays undersaturated for a greater distance along its length. And so the fracture widens faster, which allows it to carry still more water. The advantage compounds. Over a period usually reckoned in thousands to tens of thousands of years, one root among many pulls ahead until the water passing through it is still capable of dissolving rock when it reaches the far end. That moment, which speleologists call breakthrough, changes the pace of everything. Flow becomes turbulent, discharge rises sharply, the whole length of the conduit enlarges at once, and neighboring fractures are progressively robbed of their water and left as blind, decorated dead ends. A cave in this sense is a fracture that won. After breakthrough, the rates are still modest by human measure. Enlargement of an actively flowing limestone conduit is usually a fraction of a millimeter a year on each wall, occasionally rather more where discharge is large and the water aggressive. A tube 5 meters in diameter therefore represents something on the order of tens of thousands of years of steady work, and a system of many kilometers of such passage, developed through several distinct phases, commonly represents hundreds of thousands. Where the surface above is wearing down at the same time, the two processes are linked, and measurements of dissolved load in karst springs in wet, temperate regions suggest overall lowering of the limestone landscape at a few tens of millimeters in 1,000 years. The shape of a passage records the conditions in which it grew. Below the water table, where the conduit is permanently full, water presses on the whole perimeter and the cross-section tends towards a circle or an ellipse, often with the walls sculpted into shallow, asymmetric scallops whose size reflects flow velocity and whose steeper faces point upstream so that direction of an ancient current can be read long after the water has gone. Above the water table, in the vadose zone, a stream flows with a free surface and cuts downwards, incising a narrow, tall canyon in the floor of whatever it inherits. Where a rounded tube has later been drained and a stream has trenched its floor. The result is the keyhole cross-section, a circle above and a slot below, which states in the rock that the water table fell. That falling is usually the work of the surface rivers. As a valley cuts down, it lowers the level to which the underground water can drain, and the water table falls to follow it, abandoning the upper conduits and initiating new ones lower in the rock. Long-lived karst areas accordingly contain caves arranged in tiers, dry and dusty and full of calcite near the top, active and wet at the bottom. And the levels can sometimes be matched to river terraces outside. Ages are obtained by dating the calcite that formed once a passage drained, by uranium series methods on flowstone that caps a sediment layer, which gives a minimum age for the passage beneath, and such work has established that some familiar systems were already being drained well over 500,000 years ago. Dissolution alone rarely accounts for the large chambers. Once a void is wide enough that the rock above cannot bridge it, blocks part along bedding planes and joints and fall, and the ceiling migrates upwards while a pile of breakdown accumulates below, until either a stronger bed arrests the process, or the collapse reaches the surface and opens a sinkhole. Limestone is not the only soluble rock either. Gypsum dissolves faster and in water needing no acid, salt faster again and so seldom survives, and dolomite more slowly than limestone. In parts of the Guadalupe Mountains of New Mexico, the evidence points to a different agent altogether: hydrogen sulfide rising from depth and oxidizing near the water table to sulfuric acid. A reaction that leaves thick masses of gypsum behind as a byproduct and that produced chambers with no connection to any surface stream. The same chemistry that hollows the rock runs backwards a little further along its path, and everything that grows in a cave grows because of that reversal. Rainwater sinking through soil takes up carbon dioxide from decaying plant matter and root respiration, reaching concentrations far above those of the open air. And this weakly acidic water dissolves limestone as it moves down through fractures. When it emerges on a cave ceiling, it meets air that holds much less carbon dioxide, and the gas begins to leave the water, exactly as it leaves an opened bottle, though far more slowly. As the carbon dioxide escapes, the water can no longer hold the calcium and carbonate it was carrying, and calcite crystallizes out on whatever surface the water happens to be touching. Evaporation contributes in drier passages, but degassing does most of the work, and the whole family of cave deposits, the speleothems, follows from it. The simplest form begins at a single drip point. Water gathering at the tip of a hanging drop loses gas from its surface, and a ring of calcite is deposited around the drop's circumference, so that the next drop hangs from a slightly longer rim, and the next from a longer one again. What grows downwards is a hollow tube with walls a fraction of a millimeter thick, and an internal diameter set by the size of the drop, close to 5 millimeters in most caves, which is why soda straws in caves thousands of kilometers apart look so much alike. Some reach several meters in length while remaining as fragile as they sound. When the central canal becomes blocked by a crystal growing across it or by sediment, water is forced to run down the outside, and the tube thickens into the tapering, layered stalactite of common description, its concentric growth rings arranged around the old straw at the center. Water that falls before it has given up all its dissolved load carries the remainder to the floor, where it splashes, loses more gas, and builds upwards without any central canal, since the supply arrives at the top from outside rather than through the middle. The shape of a stalagmite records the conditions of its feeding. A slow, steady drip from a low ceiling produces a rounded dome. A faster drip falling further tends to produce a narrow, near-cylindrical column, sometimes called candlestick form, whose diameter stays remarkably constant for as long as the drip rate does. A very fast flow spreads out and makes a broad mound, and one that is intermittent may build knobs and terraces. Where a stalactite and the stalagmite beneath it meet, they fuse into a column, and thereafter the water runs down the outside of a single continuous mass of calcite. Films of water spreading across walls and floors leave flowstone in sheets and folds, thick enough in places to seal a passage entirely. Where a film crosses a slight lip and becomes turbulent, it loses carbon dioxide preferentially at that line, so calcite builds along the lip and raises it, and the raised lip ponds the water behind it, which slows and deposits more, so that the floor of a wet gallery may end up divided into a staircase of shallow basins behind rimstone dams. In pools where the water sits quietly, crystals grow inwards from the sides and bottom in flat-topped plates, and any object left in the water for long enough acquires a coating of calcite spar. Calcium carbonate has a second common crystal form. Aragonite, identical in composition and different in structure, favored where the water is rich in magnesium or where evaporation is rapid, and it grows as needles, sprays, and radiating tufts rather than in blunt layers. Aragonite is not stable over long spans in cave conditions and gradually converts to calcite, a change that recrystallizes the deposit and destroys the fine detail of its layering, which is one reason those studying past climate prefer to work with calcite that has never been aragonite. There are also deposits that grow as knobbly clusters, sometimes called cave popcorn, generally where water seeps from many small pores across a wall or where air movement drives evaporation, and there is moonmilk, a soft white paste of microscopically fine calcite crystals and water that holds together like wet chalk, and in which microbial populations are abundant. Not everything obeys gravity. Helictites are slender, twisting growths that leave a wall or the side of a stalactite and wander sideways, upwards in loops and hooks, apparently without regard for the vertical. Their central canal is very much finer than a soda straw's, fine enough that water is drawn along it by capillary force and arrives at the tip too slowly to form a hanging drop at all, so it simply evaporates and degasses where it emerges, and the growth extends in whatever direction the crystal at the tip happens to favor. Impurities, small blockages, and the orientation of individual crystals all appear to redirect the growth, and while the general mechanism is well accepted, the details of why a particular helictite turns where it does remain incompletely explained, where the rock or the sediment supplies sulfate rather than only carbonate, and where the passage is dry enough that no film of water washes the walls, gypsum crystallizes instead. It grows in a manner unlike calcite, not by addition at the outer tip, but by extrusion at the base, with new material forming where pore water reaches the wall surface and evaporates, pushing the older crystal outwards. Fibrous bundles emerge and curve as they lengthen, producing the forms called gypsum flowers, along with needles, hair, and cotton so light that a movement of air can disturb them. The dry, sulfate-rich caves of the Guadalupe Mountains contain gypsum in blocks, crusts, and long pendant masses, preserved only because liquid water has not returned to those passages, since gypsum dissolves readily and would not survive a wet phase. Cave pearls form in shallow basins fed by a drip vigorous enough to keep the water moving. A grain of sand or a fragment of calcite acts as a nucleus, and concentric layers of calcite accumulate around it, while the agitation keeps it from cementing to the floor of the basin, turning it over often enough that it grows in all directions. Some are almost spherical, others flattened or polygonal where they have been packed against neighbors, and in some basins they lie in nests of dozens, their surfaces smooth from constant contact. If the drip stops or shifts, the pearls cement in place and the process ends. The reason so much attention has been given to these deposits beyond their appearance is that they keep time. A stalagmite sawn lengthwise and polished shows layering, and where the water supply varies seasonally, the layers are annual, sometimes visible as alternating clear and cloudy calcite, sometimes only under ultraviolet light, where organic acids washed in during the wet season fluoresce as fine, bright lines. Thickness varies with the rate of supply, so a sequence of thick and thin layers is a record of wetter and drier years, and a break in the layering, a hiatus, marks an interval when the drip failed altogether, or when the surface film dissolved rather than deposited. Absolute ages come chiefly from uranium series dating, which works well here because uranium is soluble in the seeping water and thorium is not. So calcite starts out with uranium and almost no thorium, and the thorium that accumulates afterwards comes from radioactive decay. Measuring the ratio gives an age with useful precision back to something like 500,000 years. And modern instruments need only a small sample, a few tens of milligrams, so a single stalagmite can be dated at many points along its length. Radiocarbon is less straightforward because some of the carbon in the calcite comes from the limestone itself and is far older than the deposit. The layers also hold chemical records. The ratio of oxygen isotopes in the calcite depends on the isotopic composition of the rainfall that fed the drip and on the temperature of the cave, so it responds to changes in the source of moisture, the amount of rainfall, and the atmospheric circulation delivering it. Carbon isotopes reflect the vegetation, and biological activity of the soil above. Trace elements such as magnesium and strontium tend to rise when water spends longer in the rock and deposits calcite before it arrives, which happens in drier conditions. Tiny pockets of the original water trapped as fluid inclusions during growth can be extracted and analyzed for the temperature at which they were sealed in. From such measurements, records of monsoon strength, of glacial and interglacial alternation, and of abrupt shifts that match those seen in polar ice have been assembled, sometimes from a stalagmite already broken by an earthquake or a rockfall long before anyone entered the passage. A surface stream running over shale or granite behaves in a way that can be watched from the bank. But where it crosses onto limestone, it often begins to lose itself. First, through cracks in its own bed, so that in dry weather the channel downstream lies empty and dusty, and then, at some final point altogether, into a slot or a boulder-choked hollow at the base of a low cliff. The place where it goes has different names in different countries. A swallet or a swallow hole, a ponor, a sink, and standing at one of them, the sound of water is audible for a while below the stones and then is not. Somewhere lower in the landscape, perhaps in the next valley, water comes out again at a spring, clear or milky depending on the weather, and the question of whether it is the same water occupied hydrologists and cavers for a long time before it could be answered. The instinct to put something into the water and wait for it to reappear is old. Chaff, sawdust, brick dust, and salt were all used, along with substances that could be tasted or measured rather than seen, and the results were often ambiguous because the material was diluted beyond recognition, or filtered out by sand, or simply missed by an observer who had gone home before it arrived. Salt could be detected by taste and later by the electrical conductivity of the spring water, which gave a real measurement rather than an impression, but it needed to be added in quantity. And quantity is a difficulty when the receiving spring may be many kilometers away and discharging steadily throughout. The material that changed the practice was a synthetic dye, fluorescein, first prepared in the 1870s, which is intensely fluorescent in dilute alkaline solution, giving a green glow to water in which the color itself has become invisible. In 1877, dye was poured into the losing bed of the upper Danube, where the river sinks into fissured limestone, and it appeared at a large spring belonging to a different river system, the water having crossed beneath the watershed on its way towards the Rhine rather than continuing towards the Black Sea. The result was not a curiosity of local interest. It established that in karst, the surface drainage divide need not correspond to anything underground, and that catchments defined on a map by contours could be entirely wrong. Tracing since then has become careful work with a written protocol. The dye is weighed and mixed and introduced at a known time, usually with a chaser of water to flush it through the shallow zone, and at the springs and wells that might receive it, samplers are installed, either automatic bottles on a timer or small packets of activated charcoal suspended in the flow, which absorb dye continuously and can be collected and eluted later in the laboratory. Fluorometers measure concentrations far below the threshold of the eye, and by taking many samples through time, a breakthrough curve can be drawn. Its first arrival, its peak and its long tail, each saying something about the geometry of the route, whether a single conduit or a set of parallel paths, whether storage in pools slows the passage or a clean pipe carries it through, where several sinks are being tested at once, different dyes are used, or spores of club moss sieved to uniform size and stained in several colors, caught in nets at the springs and counted under a microscope. The results, accumulated across many karst regions, describe a drainage that ignores the surface almost entirely. Water sinking on one flank of a hill has been shown to emerge on the other. Single sinks feed two springs at once, and the proportion between them shifts as the water table rises, because in flood, an overflow route higher in the rock is brought into use. Transit velocities are frequently a kilometer a day or more, and in flood conditions far quicker than that, which is to say that water moves through a limestone aquifer at speeds closer to those of a stream than to the slow seepage through sand that classical groundwater theory describes. In the karst above the Gulf of Trieste, the river that sinks beneath the Scotian caves has been linked to great springs near the coast a considerable distance away, and the linkage was established by tracing long before the whole of the intervening course had been entered by anybody. Entering it is the other half of the work. In the 1930s, divers in the Mendip Hills in England went into the flooded passages of Wookey Hole wearing borrowed heavy diving dress, breathing air pumped down a hose from the dry chamber behind them, and walking on the floor of the submerged canal with weighted boots tended by a line party who could feel their signals. In 1936, in a nearby cave, a homemade dry suit allowed a diver to pass the first flooded section of Swilden's hole and surface in the passage beyond, which is the essential maneuver of all sump exploration, because the reward is not the dive itself, but the air-filled cave on the far side. A group dedicated to cave diving was formed in England shortly after the Second World War, and on the continent, the newly available open-circuit demand valve was taken into the Great Spring at Vaucluse in the same period. With mixed results, the equipment and the understanding of gas both being new. The technique settled into something recognizable. A guideline is laid from a reel and belayed to projections as the diver goes, because visibility can be lost in a moment when fine silt is stirred from the floor by a fin, and in that condition the line is the only route back. Gas is planned so that a substantial reserve remains after the turn, typically with rather more than a third held back for the return, since a diver in a sump cannot ascend and cannot in general be met by anyone. Cylinders are carried at the sides rather than on the back, so that low restrictions can be passed and a valve can be reached and shut off by hand. and spare sets are staged along the route for the return journey. Closed-circuit rebreathers, which recycle exhaled gas and absorb the carbon dioxide chemically, extended range considerably, because the volume of gas needed for a long dive ceases to be the limiting factor, and they disturb the ceiling less, which matters where a curtain of silt hangs ready to fall. Where a long dive requires decompression, it may be spent in an air bell, sitting in a chamber that no one will visit again for years. Many sumps in dry caves are short. Some are ducts that can be passed with the face turned up in a few centimeters of airspace. Others need a free dive of a few meters without apparatus, and a great many lie at the end of kilometers of crawling and climbing, so that the diving equipment has to be dragged there in bags before anything can begin. Levels shift with the season, and passages that are flooded in winter can be walked in a dry summer, which has made drought a form of opportunity, and in some systems, sumps have been pumped down deliberately to open a way. Detailed records of these obstacles, their length, depth, and the state of the water beyond are kept region by region. The reverse approach starts at the spring and works upstream against the flow, which puts the current in the diver's face on the way in and behind them on the way out, and turns the resurgence itself into an entrance. Springs of this kind often prove to be the top of a shaft rather than the end of a horizontal passage, the water having risen from depth under pressure, and the exploration then becomes vertical, with the constraints of depth and decompression added to those of distance. At Vaucluse, where the water emerges at the foot of a cliff and where early dives had gone only a modest way, a remotely operated vehicle lowered on a cable in the late 1980s reached the floor of the shaft at more than 300 meters below the surface, a depth no diver had approached there. In the limestone platform of the Yucatan, where the sea has held the water table close to the surface and collapse has opened cenotes at intervals across the forest, divers working from those pools have surveyed flooded galleries running for hundreds of kilometers in single connected systems, passing through the boundary layer where fresh water floats on salt water, and the two remain visibly separate. Progress there is measured in surveyed line, foot by foot, laid and tied and later reduced into maps, and the joining of two named systems by the discovery of a single connecting passage can add tens of kilometers to a total at a stroke. Even without diving, the water leaves its account of itself on the walls. Scallops, the shallow asymmetric hollows cut into limestone by turbulent flow, are steeper on their upstream side, and their size varies inversely with the velocity of the water that formed them. So a passage long since abandoned by its stream can be read for both the direction and the approximate speed of a current that stopped running before anyone was there to see it. Keyhole cross-sections record a tube filled with water that later drained and had a canyon cut into its floor. Foam, twigs, and fine mud lodged high on the ceiling record the level of the last flood, and gauging the spring through a storm, watching how quickly it rises and how much sediment it carries, gives a measure of how directly it is connected to the surface. That connection is the practical reason much of this work is funded, since water arriving at a spring in a day or two has not been filtered by anything, and knowing which fields and roads drain to which spring is the beginning of protecting it. The same passages that carry the water carry the animals, and the first thing that anyone notices on entering the dark zone of a cave with a good lamp is how little there is to see. A stream in daylight would be busy with insects and algae and the shadows of fish. A stream half a kilometer inside a hill runs over clean rock with almost nothing on it. And what living things there are must usually be looked for deliberately in the film of water on a flowstone, under a stone at the edge of a pool, on the underside of a piece of waterlogged wood brought in by a flood. Caves are conventionally divided into an entrance zone that still receives light and daily weather, a twilight zone where green plants thin out and disappear, and a dark zone in which the temperature holds near the mean annual temperature of the surface above, and the air stays close to saturation, and it is in that third zone, with its constancy and its poverty, that the specialized animals live. Cave biologists sort those animals by how far their lives depend on the cave, rather than by where a single individual happens to be found. And the scheme they use was first proposed in the middle of the 19th century and refined in the early 20th. Troglodytes enter caves and leave them, using the shelter for part of a cycle that still requires the surface, as bats do when they hibernate in a cold gallery and feed in the open air, and as moths and certain flies do when they gather near an entrance to overwinter. Troglophiles can complete their whole life in a cave and also live in damp, dark, sheltered places outside it, under logs and stones and in the soil. Troglodytes live only in caves and in the cracked rock and gravels connected to them, and cannot survive on the surface at all. The aquatic obligates are often given their own name, stalagmites, after the underground river of the Greek underworld, and the distinction matters practically, because the water-filled voids of a limestone mass are a far larger habitat than the walkable passages and hold most of the species. What makes obligate cave animals recognizable at a glance is a set of features that have appeared over and over in unrelated groups, which is why the pattern was named before it was explained. Eyes are reduced or absent, sometimes to nothing more than a pigment-free spot beneath the skin. Body pigment is lost, so that the animal appears white, ivory, translucent, or faintly pink from the blood beneath. Antennae, legs, and sensory bristles are longer and finer than in surface relatives, spreading the sense of touch and of chemistry over a wider volume. Metabolic rates are low, and starvation is tolerated for long periods. Growth is slow, maturity late, eggs few and large, and lifespans in some cases very long. The suite is called troglomorphy, and its consistency across fish, salamanders, beetles, crustaceans, and spiders is one of the reasons cave faunas have been used so often as a natural experiment in evolution under a single, severe, and unusually stable set of conditions. The formal study of that fauna is usually traced to a small blind beetle found in the caves at Postojna, in the karst of what is now Slovenia, by a local guide working with the lamps that lit the show passages and described by a naturalist in the 1830s. It was long-legged, eyeless, and pale, with a swollen abdomen, and it did not resemble anything known from the surface. The find drew collectors into the Slovene and Croatian caves for the rest of the century, and the practice of describing subterranean animals became organized enough to acquire a name, biospeleology, from a Romanian zoologist and a French colleague whose essay on the problems of underground life appeared in the first decade of the 20th century. An institute devoted to the subject was founded in Romania in 1920, the first of its kind, and from then on the cataloguing proceeded much as the surveying did, cave by cave and season by season, with specimens preserved in alcohol, labeled with the name of the cave and the date, and deposited in museums where later workers could re-examine them. The blind fish came into the literature by the same slow accumulation. In the limestone of the interior of the eastern United States, in Kentucky, Indiana, Tennessee, Missouri, and Alabama, a small family of cave fishes lives in streams and pools within the rock, growing to a few centimeters, without functional eyes and almost without pigment, moving in unhurried curves through still water. Their skin carries rows of small sensory papillae arranged in lines along the head and body, which respond to water movement and allow a fish to hold its position to detect the disturbance made by a copepod and to map the walls of a pool by the way its own swimming displaces water. In at least one of these species, the eggs are reported to be carried and brooded in the gill chamber of the female, a habit that would keep a small number of offspring safe in an environment where a spawning bed on open gravel offers little protection and little food. The same family includes a surface-living relative in swamps and ditches, with eyes and pigment intact, which makes the comparison between the states unusually direct. The other much-studied fish is a tetra from the limestone hills of northeastern Mexico, where a river-dwelling form with normal eyes and silvery color occurs at the surface, while separate populations in a series of caves within the same rock are pale and eyeless. The two remain the same species in the sense that they can be crossed, and their embryos show something instructive. A cave-form embryo begins to build an eye, forming a lens and the beginnings of a retina, and then the lens tissue dies away and the whole structure regresses and is covered over by skin as the fish grows. The cave populations also carry more taste buds on the head, a wider jaw, and behavior that draws them towards vibrations in the water rather than away from them. Some of the changes appear to come from the accumulation of mutations that nothing selects against once vision is useless, some from the saving of energy spent on tissue that is expensive to build and run, and some from the fact that the signaling pathways which reduce the eye also widen the mouth and multiply the taste buds, so that a single change carries loss in one organ and gain in another. Salamanders occupy the same waters elsewhere. In the Dinaric karst of the eastern Adriatic, a pale, slender amphibian, nearly the length of a forearm, lives in flooded passages and is occasionally washed out of springs after storms, which is how it first became known to naturalists, described in print in the second half of the 18th century after centuries of local report. It keeps its larval form throughout life, breathing through feathered external gills held out on either side of the head, as well as through skin and lungs, and its eyes are reduced and covered. It grows slowly, breeds rarely, and appears to live for a very long time, well beyond the span of most amphibians, on a diet of small crustaceans and worms taken from the water. A dark, functional-eyed population is known from a limited area of the same region, which suggests that the pale form's condition is a consequence of the habitat rather than an inheritance shared by the whole lineage. In the Ozark Plateau of the central United States, there is a salamander that reverses the sequence, hatching in surface streams with working eyes and pigment, then moving into caves, losing pigment and having its eyelids fuse over degenerating eyes at metamorphosis, so that a single animal passes from sighted larva to blind adult. In the caves of Tennessee and neighboring states, other species hold their gills into adulthood in the same way as the dinaric animal, pale and slow in shallow pools. Most cave animals, though, are small and unremarkable to look at, and the bulk of the catalogues is made of them. Springtails, the wingless hexapods that live in soil and leaf litter everywhere, are among the most consistently present, with cave forms that have lost their eye patches and pigment and carry antennae longer than in their surface relatives, feeding on fungal threads and on the films of decaying organic matter that collect wherever water has stood. With them come dipluran and campodeiid two-pronged bristletails, mites, pale woodlice, millipedes, harvest men with legs several times the length of their bodies, spiders that build small sheet webs in drafty spots, beetles that hunt across mud banks. And in the water, amphipods, isopods, copepods, ostracods, and blind shrimps. Nearly all of it depends on energy brought in from outside, in the guano of bats and cave-nesting birds, in the wood and leaves and drowned earthworms carried down by floods, in tree roots that reach through the ceiling into a shallow passage, and in the dissolved organic carbon that arrives in seepage water and is taken up by microbes on the walls. Finding these animals is a matter of technique as much as of patience. Collectors work slowly along a passage with a headlamp and a hand lens, turning stones and replacing them, examining the meniscus of drip pools where small crustaceans gather, and setting baited traps of cheese, liver, or rotten wood to be recovered on a later visit. For the animals of the water-filled cracks, which are not reachable by walking, a hole is dug in the gravel beside a stream, and the water that seeps into it is scooped and filtered, a method devised in the early 20th century and still in use, later supplemented by hand pumps that draw water from a driven pipe. Wells, boreholes, and spring outflows are sampled with nets, and the material is sorted under a microscope. Endemism in these faunas is high, with many species known from a single cave or a single group of springs, so descriptions often rest on a handful of specimens and on very fine differences in the shape of a limb or a mouthpart. And molecular comparison has since shown that some widely distributed named species are in fact clusters of local ones that look alike. The films themselves turned out to be more than a coating. In a cave in southern Romania, opened by excavation in the 1980s, the air above the water holds hydrogen sulfide, methane and carbon dioxide, and very little oxygen. And the community there is supported not by anything washed in from the surface, but by bacteria that oxidize sulfur and methane, building organic matter from chemical energy in complete darkness, with mats floating on the water and a set of invertebrates, many of them found nowhere else, grazing on them. Elsewhere, in the sulfurous caves of Mexico and in the deep chambers of the Guadalupe Mountains in New Mexico, biofilms hang from the ceilings in soft drips that carry a fluid acidic enough to burn skin and clothing, and the pale corrosion residues on the walls are populated by microorganisms that appear to take part in dissolving the rock as well as living on it. Cave microbiology has accordingly become part of cave geology, and the walls of a passage are now sampled with swabs and sequenced as a matter of course, which has added to the catalogue a great many organisms that no lamp will ever show, and confirmed that even galleries with no visible inhabitants at all are not empty. Depth, in the language of cave exploration, is a measured quantity rather than an impression, and it means the vertical distance between the highest entrance of a system and the lowest point that has been surveyed within it, which is why a cave becomes deeper by being explored rather than by changing in any way itself. The consequence is that the list of the deepest known caves is a record of expeditions and of the arithmetic of survey books, revised whenever a team descends a new shaft at the bottom of an old one, and adds another few tens of meters to a total. And it has been dominated for the last several decades by a small number of massifs where thick limestone stands high above the level at which its water emerges, which is the geometrical condition for great depth. Almost all of the systems that pass a kilometer lie in the Alps, in the Pyrenees, in the mountains of Mexico, and in the Western Caucasus. The first cave explored below 1,000 meters was the Gouffre Bergère, in the Vercors of France, found in the early 1950s by a local caver whose name the cave carries, and pushed within a few seasons through a series of shafts and a large streamway to a depth beyond that figure. The expeditions that did it were large and slow, involving many people carrying wire ladders and hemp, and later nylon rope, laying telephone wire as they went so that the surface could be told what was happening, and setting up underground camps on gravel terraces beside the river. For some years afterwards, the Bergère was the standard against which deep caving measured itself, and the techniques worked out in it, particularly the practice of stocking a camp in advance so that a small team could sleep and eat at depth rather than turning round, became the ordinary method of deep exploration. In the Alps, the search moved to high limestone plateau, where the entrances lie above the tree line at 2,000 meters or more and are often blocked with snow until midsummer, so that the exploring season is a matter of weeks. In the Haute-Savoie, two systems in particular, the Réseau Jean Bernard and the Gouffre Mirolda, were pushed past 1,600 meters in a long series of campaigns from the 1970s onward, and they exchanged the position of deepest known cave between them more than once as new surveys were completed and old ones corrected. The Austrian Alps produced another kind of result at Lamprechtsofen in the Salzburg limestone, where the exploration proceeded upward from a low entrance rather than downward from a high one, climbing shafts from the inside with bolts and ladders over many years, until a connection was made with a higher entrance on the mountain above, and the full vertical range of the system, more than 1,600 meters, could be counted. The Caucasus entered the record later, and then held it. On the Arabica Massif, in the mountains behind the Black Sea coast, the limestone is several kilometers thick, and the water that sinks into its high pastures has been traced to springs at and below sea level, which told the surveyors of the 1960s and 70s that a very deep system existed somewhere in the rock, whether or not a human passage led into it. Soviet and then Ukrainian, Russian and international teams worked the massif shaft by shaft for decades. And in 2004, one of those shafts, Krubera, also known as Voronia, was pushed beyond 2,000 meters, the first cave anywhere known to reach that depth. Later expeditions in the same massif turned a nearby entrance, Veryovkina, into a system deeper still, a little over 2,200 meters, and the two caves lie within a few hundred meters of each other on the surface, without any explored connection between them. Mexico offered a different problem. In the Sierra Mazateca of Oaxaca, the limestone rises steeply above deep river canyons, and the caves that drain it, above all Sistema Huautla and Sistema Cheve, are entered high and descend through long series of pitches into active streamways that carry a great deal of water in the wet season. Huautla was explored from the 1960s onward by successive expeditions that connected several entrances into one system and pushed it past 1.5 kilometers of depth, and its lower reaches end in water-filled passage, so that further progress required cave divers to carry cylinders down through days of vertical ropework, and then dive from an underground camp, which they did across several campaigns. At Chev, dye placed in the stream reappeared at a resurgence far below and far away, indicating a vertical range for the whole hydrological system considerably greater than what has been walked and climbed, and expeditions have continued to work at the bottom of the explored part in the hope of joining the two. What the descent itself involves has changed less than the depths reached. A deep cave is rigged with rope in pitch lengths of tens of meters, each anchored to bolts placed in sound rock with a hand drill, or, more recently, a battery drill, and divided by rebelets so that no single length of rope hangs long enough to stretch dangerously or to rub against the wall. Every kilogram that goes down in a tackle sack clipped beneath the caver, and the sacks contain rope for the pitches below, food, stoves, fuel, spare lamps and batteries, dry clothing sealed in waterproof drums, survey instruments, and the tents and sleeping bags for the camps. A serious expedition to 2,000 meters may place 3 or 4 camps at intervals down the cave, each stocked over several carrying trips before anyone attempts to live in it. And the logistics of moving that material occupy far more of the expedition's time than the actual exploring at the bottom. A camp is chosen for dryness, for a floor of sand or gravel that can be leveled, for a supply of drip water or a clean pool, and above all, for height above the streamway, since a passage that floods to the ceiling is uninhabitable no matter how convenient it otherwise looks. Tents are pitched inside the cave not against rain, but against draft and against the constant fall of condensation from the roof. And they hold warmth well because the air inside them is warmed by the people in it. In the high Alps, a camp may sit at 2 or 3 degrees above freezing, while in the deeper Caucasus systems the rock warms with depth and the lower camps are milder. Though the humidity everywhere is close to saturation, so that nothing left out ever dries and clothing is kept in sealed containers until the moment it is worn. Living underground for 2 or 3 weeks produces a set of ordinary difficulties. Without daylight, sleep tends to lengthen and drift, and teams either keep to watches and a written schedule or let their days stretch to 28 or 30 hours, which is common enough that expedition logs record the discrepancy between camp time and surface time. Appetite falls in the first days and then rises, and food is calculated in advance at several thousand calories a person a day, chosen for weight, for keeping without refrigeration, and for cooking in one pot on a small stove. Skin softens and does not heal well in permanent wet, so small cuts on the hands are treated seriously, and human waste is bagged and carried out along with every empty packet, because a camp used for years by successive expeditions would otherwise become unusable. The exploring itself, when it happens, is a few teams of 2 or 3 working shifts below the deepest camp, rigging new pitches, following the water, and surveying as they go with tape or laser rangefinder, compass and clinometer, so that the depth claimed at the end is a sum of measured legs rather than an estimate. Flooding is the principal hazard, and it is met by rigging above the level of the stream where possible, by watching the weather on the surface and passing word down by wire or by relay, and by waiting, sometimes for a day or two, in a dry chamber above a flooded section. Exiting from 2,000 meters takes a fit and rested caver a long single push, or, more often, 2 days with a night at an intermediate camp. And after the last team is out, the ropes have to be recovered, which means that the final work of an expedition is to climb the whole cave again, unrigging it pitch by pitch on the way. Not every cave is made by removal. The systems described so far are hollows left where rock has been carried away in solution, molecule by molecule, over spans of time long enough that the water which began the work has long since left the ground. But there is a second family of caves that comes into being almost at once, in the course of hours or days, and is built rather than dissolved. These are lava tubes, and they occur wherever basaltic lava, which is hot and fluid and poor in silica, runs downhill in a sustained flow for long enough to roof itself over. Their study belongs to volcanology as much as to speleology, and the two disciplines meet inside them, because a lava tube is at the same time a cave to be surveyed and a fossil record of how a particular eruption moved its material across the landscape. The process is understood in reasonable detail because it has been watched from the outside many times on the island of Hawaii. A flow of the smooth, ropey kind that Hawaiian usage calls pahoehoe loses heat fastest at its upper surface, where a thin elastic skin forms and thickens, and along the margins where levees of chilled lava build up on either side of the moving stream. Given time, the skin and the levees meet and close over the top, and the flow continues inside an insulated conduit, losing very little heat over long distances, which is why lava can travel many kilometers from a vent and still arrive molten. When the supply from the vent falls away, the remaining lava drains downslope and the conduit is left empty. A tunnel with the floor of congealed lava, walls sometimes glazed by a final rush of heat, and a roof that may be only a meter or two thick. Entry into such a cave is almost always through a collapse. Portions of the roof fall in, either while the tube is active, producing openings through which the moving lava can be seen, or later under the weight of subsequent flows and the slow decay of the rock. And it is these skylights and collapsed trenches that give explorers a way down. In Hawaii, Volcanoes National Park, a short and well-lit section of tube is walked through by visitors every day, while elsewhere on the same island, longer systems have been mapped by volunteer groups working with tape and compass in the ordinary way. And one of them, following a flow down the eastern flank of Kilauea, has been surveyed to a length of several tens of kilometers, which makes it among the longest lava tubes known anywhere. The mapping is patient work because the passages branch, rejoin, run one above another, and are frequently blocked by breakdown that has to be pushed through or bypassed. Inside, the decoration is made of the same rock as the walls and formed in minutes rather than millennia. Drips of molten lava hanging from the ceiling chill into short stalactites, sometimes with matching mounds beneath them where the drops fell, and the resemblance to their limestone counterparts is only in shape, since these grew by cooling rather than by deposition from solution. Along the walls run horizontal ledges and benches that mark levels at which the flowing lava stood for a time, in the way that flood marks record river stages, and in places a smaller tube has formed inside a larger one after the level dropped. Later on, water seeping through the roof brings in mineral coatings of gypsum, calcite, and various sulfates, so that a lava tube a few centuries old may carry a faint pale crust that has nothing to do with volcanism. Iceland has its own tubes, formed in the basalt flows that cover much of the interior, and several have been known and used since the settlement period. The Hallmunda Hraun lava field, west of the great interior ice fields, contains a set of long tubes that were described in early written accounts and that still hold traces of human use, including stone structures inside the dark zone whose purpose has been debated by archaeologists. Others closer to the capital are entered through collapses in the middle of open lava, with the surrounding ground rough enough that walking to them takes longer than walking through them. Because the Icelandic climate is cold and the roofs are thin, many of these caves hold ice for much of the year, and floors of clear layered ice, columns fed by dripping meltwater, and rime crystals on the walls are ordinary features, which gives the odd result that a cave made by fire is most impressive when frozen. Lava tubes are also inhabited, and in Hawaii, the inhabitants have been catalogued with some care. Tree roots penetrate the thin roofs and hang into the passages in curtains, providing the base of a food chain that includes plant hoppers which feed on root sap, small predatory spiders, crickets, and a variety of beetles, many of them without functional eyes or pigment and closely related to surface species living in the forest overhead. What makes them of particular interest is the age of their habitat, since some of these caves are only a few centuries or a few thousand years old, which sets an upper limit on how long the loss of eyes and color can take. The walls themselves carry microbial films, faintly gold or bluish under a lamp, living on minerals and on whatever organic matter the water brings down. Ice makes caves too, and by a mechanism closer to limestone than to lava, since it involves a soluble solid and running water, though the solvent is simply heat. On a temperate glacier, surface meltwater collects in streams that eventually find a crevasse or a weakness and cut down into the ice, forming a vertical shaft called a moulin. And from the base of that shaft, the water works its way along the glacier bed or through the body of the ice towards the snout. The resulting conduits can be large enough to walk through, and in Iceland and the Alps, they are entered in winter, when melting has slowed and the water inside has dropped to a trickle. The ice is often free of bubbles and transmits light in a deep blue, because it absorbs the longer wavelengths and leaves the shorter ones to scatter through, and the walls are scalloped in the same way as the walls of a limestone stream passage. Glacier caves have to be resurveyed constantly because the ice moves and the passage shapes change from one season to the next, and a route mapped in one winter may be closed or entirely rearranged by the following one. Some groups have used laser scanning to record whole cave interiors as point clouds, partly for their own sake and partly to measure how quickly the volumes change, which bears on the behavior of water beneath the glacier. Where a glacier lies over volcanic ground, geothermal heat melts caves from below and keeps them open through the summer, with warm air and steam moving through them and, in places, sulfurous gas that has to be checked for before entry. The extension of all this beyond the Earth began with photographs of long, sinuous channels on the Luna Maria, some of them with sections that appear to have been roofed, which suggested that the same tube-forming process had operated in the ancient basalt flows of the Moon. Later orbital imaging found something more direct: circular pits, tens of meters across and tens of meters deep, in several of the Mare regions, first noticed in images from a Japanese lunar orbiter, and then photographed obliquely at high resolution by an American one, so that in a few cases the overhanging edge of a floor could be seen extending sideways under the surrounding surface. Gravity measurements from a pair of satellites flying in formation have been interpreted as showing mass deficits along some of the sinuous reels, consistent with buried voids, and because lunar gravity is about a sixth of the Earth's, structural modeling allows lunar tubes to be far wider than any that could stand on Earth. Mars shows similar features on the flanks of its great Tharsis volcanoes, where thermal infrared imaging first drew attention to small dark holes that stayed relatively warm at night, and higher resolution cameras later showed them as steep-sided pits, some with visible floors of fallen debris and some without any floor visible at all. Chains of aligned pits run for kilometers across the volcanic plains, and whether they mark drained lava tubes or fractures pulled open at depth is decided case by case, often without a firm answer. The interest in them is practical as well as geological, since a few meters of rock overhead would cut the radiation dose considerably and moderate a surface temperature that swings widely between day and night. And this is one reason space agencies have sent astronauts to train in terrestrial caves, moving in small teams through unfamiliar dark passages, surveying, sampling, and living for days on what they carried in. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well and see you very soon.